I should get a little better, right?
All right, so the lesson today is on intermolecular forces. So let's start there. This is a summary slide, so I'm going to let you take this down for a minute, and then I'll start kind of getting into the details. My goal for you today is to understand the difference between what we've been learning, which are intramolecular, meaning within molecules or structures, ionic, covalent, metallic. The difference between those types of bonds and what we call intermolecular forces, which are in general going to be applied to understand why molecular substances form liquids and solids. So this is, like I said, just a really generic introduction that will go into detail through them. Yeah, this term van der Waals, do you remember that name? Maybe from gas laws, the van der Waals equation, which was the corrected gas law. As we said, the ideal gas law starts to fail with real gases. This is the same van der Waals. At the time, we were saying that he built an equation to treat real gases that included the attractions. Well, now we're talking about those attractions. They're collectively called van der Waals forces. And they come in a series of flavors. These are the three most important, but I will mention a few others that are basically similar, just a little bit different. The order I'm teaching them in is what I think is the most logical conceptual order. They're not in order of strength. So. We will also be using some affectionate abbreviations to refer to these, because a lot of the questions are about, can you identify which types of molecular forces are present? Can you tell which ones are the strongest? And then can you apply that to the properties when we compare materials? So instead of writing dipole all the time, we're just going to call it dip-dip. Instead of writing hydrogen bond all the time, we'll just say H bond. And instead of saying dispersion forces all the time, we'll just say disp. Or London forces is allowed. London is a person here, not the place. Okay, let's see if you've learned anything yet. Water molecule. Second water molecule. Attractions between the two water molecules. If you think about this as a polar molecule, it would be from the hydrogen side to the lone pair on the next molecule, for example. I'm using a dotted line to indicate it's weaker. Which force, if I point to two forces, I'll point to this one and I'll point to this one. Which one of these two is intramolecular, within the molecule? Which one? The first one, the top one, or the lower one? Which is the one within the molecule? The top one. So this is intramolecular. And so things like a covalent bond exist within molecules. For example, ionic bond would be intra, metallic bond would be intra. So then, why is this called an intermolecular force? If I had to define both of these in just simplest words, intra means within the molecule. Inter means between two different molecules. So you can't even talk about intermolecular forces until there's at least two different molecules. It's like trying to have a relationship when there's nobody else there. Some people try, it doesn't work out. So is there anything I've said that you find either offensive or not understandable so far? Good. Then what I'm going to do is I'm going to go through each of the three major types of intermolecular forces and talk about how do I know if that intermolecular force is present between molecules. And there can be more than one acting. You can have multiple intermolecular forces happening at the same time. So the first one, which I find to be the easiest, can I go with this, or are you guys still writing stuff?
Still writing.
Okay, I'll pause for a second while I get ready with my demonstrations. Ready? Anyway, so let's start with what we call dipole-dipole attractions. What do you think is necessary in order for there to be dipole-dipole attractions between molecules?
Polar molecules.
Bingo! Check it out. I'm gonna pull this down so you can see it better. So, if you think about a bunch of little magnets and you throw them in a box, they have a north and a south pole, they spin around until they connect opposite ends to each other and they stick together. Isn't that attraction? We've already defined the concept of polarity and what a polar molecule looks like. It has a positive end and a negative end. So a bunch of such molecules near each other should do the same thing. They should kind of spin around until their opposite ends attract, and that attraction can bring them together and hold them. That's all this is showing. So like if you look here again at this model, HCl, the hydrogen chloride molecule, is polar because chlorine, oops, sorry, I shouldn't lean on the computer screen. Because chlorine is more electronegative than hydrogen, we get a bond dipole. Molecule becomes polar because there's nothing to balance that polarity. The chlorine is negative side, and the hydrogen is the positive side. And so as these molecules interact, we should see attraction between them. So what's going to determine how strong such an interaction is? That's a big part of it, right? Because again, Coulomb's law is still true here. If we have greater polarity, as Jason suggests by the difference in electronegativity being greater, we should expect higher charge separation and therefore stronger charges, making it a stronger attraction. So ultimately, the more polar the molecule, the stronger the dipole attractions will be. That's the key. Making sense so far? Anything too crazy? Let's look at it maybe more dynamically, if I may. Here you see it happening in action. The opposite ends just kind of line up, and through those attractions are held together. Yeah.
Wait, so is it like positive and negative?
Remember a dipole, meaning a molecule that's polar, has a positive and a negative end. So if we bring these molecules near each other, those opposite ends will attract, and that attraction will hold them together. Like when you picture a glass of liquid water, what's holding the water in the glass together instead of just flying apart are the attractions between the opposite ends of the molecules. So they stick like magnets. Is that good? Okay. Any other questions about dipole attraction? Because that's all there is to it. Yeah.
Is the difference between the two, like, okay.
Yeah. Now, we have to be careful because when we have more complex molecules, like even like water. Well, water was pretty simple still. But like if you have something like ammonia, where it's trigonal, pyramidal, and it has significant polarity in the bond. Still, it's hard to tell for sure just how strong the dipole is because the shape affects it and how much net polarity there is. So you're never going to be asked to really have to compare anything but apples and apples. Like for example, if I compared, let's do, that'll work. Let's say like ammonia versus let's say something with nitrogen trifluoride. Even though these have the same shape, because the difference in bond polarities, you're going to get different net dipole. But would I expect that you can judge directly from this which is going to be stronger? I think that would be hard. So usually the questions will be like, here's a property. Now think backwards to which is stronger based on the property. Like if I told you which one had the higher boiling point, for example, that should be a way to directly tie it back to, oh, the higher boiling has the stronger attractions because it takes more to separate them. And then we could go back and look at the molecules and make the argument, you know what I mean? But just looking at them and you're like, oh, okay, there's electronegativity difference here. Yeah, that's not gonna always be that easy. Unless, like I said, it's apples and apples. Like here, if we called one of them HCl and one of them HF, it's pretty directly comparable by electronegativity. Any other questions? Okay. So the next one is also pretty simple because it's direct play off of this. After dipole-dipole attraction, which is again easy to visualize because you just have two things of opposite ends that attract, we have probably the most important in biology and in a lot of chemistry too, hydrogen bonding. 99% of the time, if you're asked something about water's properties, almost always the answer is hydrogen bonding. Okay? And water's not the only thing that does it, but it's one of the more important things that does it. Hydrogen bonding in water is why, even though water is polar and all that, this is an extraordinarily stronger version of a dipole attraction. It's a special case, if you will. Why though? What makes it stronger than the other cases? Well, the first thing you have to recognize is only 3 elements primarily, although there's some debate on this now, but 3 elements primarily cause hydrogen bonding: nitrogen, oxygen, or fluorine. I wonder why. What do those 3 elements have in common compared to all the other elements? Here, I'll give you a fill-in-the-blank question. They are the most electroblanketive.
Negative.
Yes, very good. Nitrogen, oxygen, and fluorine are the 3 most electronegative elements. Here's the next thing that's so important. What's special about hydrogen? Out of all the elements, what's special about hydrogen? That's true. What else?
Is it the least electronegative?
Not the least, but lower. But I was going to say it only has 1 electron in it, and that's it, and 1 proton. So what happens if I take an atom like oxygen, and I'm going to draw the hydrogen atom a little different for just a moment so you can really see my point. It's just a proton with 1 electron around it. That's really all hydrogen is, right? So where this is that 1s electron cloud. Now think about this. Right now, this proton of the hydrogen atom is kind of surrounded by an electron cloud, almost like a little shell. But what happens if this oxygen starts to kind of pull that this way? We're almost going to expose this proton, meaning it's going to be like uncovered. And because it's so small and positively charged, another electron pair from the next molecule can get really close to it and make a pretty strong bond. So this is a combination of 2 aspects of atomic structure coming together in kind of a sweet spot. The most electronegative element is pulling the most easily kind of bearing nucleus and pulling the electrons away and uncovering it a lot. So then the next water molecule, which is, let's say, over here, has a lone pair that can get really close to a relatively exposed proton and make a really strong attraction. So this goes beyond just a simple dipole interaction. And that's why it's given its own special name, hydrogen bonding. But be very careful. I'm going to give you examples where it happens and where it doesn't happen. It's going to look like it would, but it won't. Hydrogen bonding in this, between these molecules, yes or no? Will these bond? Should this molecule hydrogen bond to another?
No.
Yeah, at first glance it looks like yes, because it's got fluorine and hydrogen in it, right? So why doesn't it work? Very good. In this case, the fluorine is bonded to the carbon, not to the hydrogen at any point. So even though both of these are in the molecule, we can't create the effect unless the very electronegative atom directly attaches to the hydrogen. So in this case, we can't form hydrogen bonds between molecules like this. It doesn't have everything it needs. But if we look at a molecule like, let's put this one back on, ammonia, does ammonia have the ability to hydrogen bond to other ammonia molecules? Yes. Because nitrogen attaching to a hydrogen atom creates the effect at that end, and then the lone pair from the next molecule is able to attract to it. So, for example, if I wanted to show where the hydrogen bonds would form, typically again, between the hydrogen on this molecule and the lone pair on the next one. So can water and ammonia hydrogen bond to each other? Like, can I do the same thing if the molecules are different? I'm asking that kind of rhetorically, but what is the answer to my question? Yeah, absolutely. They don't have to be the same molecules to interact with these forces.
So N, O, and F are like the only atoms strong enough to like pull the
To
electron.
create this effect the way we, yes,
Okay.
for sure. Again, if you look up some more recent articles, there are some that are arguing that we see something like this with other elements as well, but we don't have to worry. All right, so again, the attraction here, for example, is also a hydrogen bond. Hydrogen bonding, as I said, is so important in biology because the tertiary structures of things like proteins and other important biological molecules are guided by hydrogen bonding. The very nature of our DNA is zipped. You remember the double coil, the double helix of DNA, how it has to unravel to be replicated and all that? That's by hydrogen bonds held together. They're strong enough to make it stable, but weak enough to unravel when it needs to build the copies and then put back together. Anywho, so far so good. We've got 2 of the 3 done. Dipole attractions happen between all polar molecules. Hydrogen bonding is a special kind of version of that that happens in very specific types of cases. The last one is the most subtle one to understand. So before we even try to approach it, I'm going to show you a quick demonstration of something you probably already know. So I was driving home one day from work and I was tired. I was going by the forest preserve and I hit a rabbit. And I didn't want the thing to die for nothing. So I sat on the road. Luckily I had my skinning stuff with me. And I just took the dead rabbit and I just carved it right there on the road, and I peeled this skin off so I'd have it for school. What? I mean, it was already dead, right?
Exactly.
Was that the true story, or did I buy this from a chemical supply? Yeah,
That's
I bought
a true
it.
story.
Sorry. So it also doubles on the weekend when I'm going out. My rock hair. Actually, the reason I have it is because I need to create some electrostatic charge. You know probably when you rub your feet, you get a shock, all that sort of.
What?
You never rub your feet on a carpet and then touch a doorknob and you get a zap?
No.
You've never been shocked?
Well, I've been shocked, but I haven't done that.
Well, it happens though,
Yeah.
even without on purpose. But my point is, I'm going to create some shock on purpose because I want to put some electric charge on this pipe. Plastic is an insulator, so when you put extra charge on it, it stays where you put it. Metals are conductors, so if you put extra charge on them, they spread out because they're free to move, so they're going to get as far as they can. Now what I'm going to do is I'm going to take two things that are totally neutral right now. I'm going to rub this pipe with the fur, and what we're expecting to happen is some of the electrons on the fur are going to get placed onto the plastic. Again, this is called triboelectricity. Not tribo, tribo. Tribo in Greek means rub, and when you rub certain surfaces together, it was known even in ancient times that they can pick up this weird ability to make things kind of attract. In other words, they were picking up an electrostatic charge. So I'm going to do it to both of these. This is styrofoam, so that's an insulator. This is a balloon that's been covered in tin foil, so it's a conductor on the outside. So first on the insulator, watch what happens. Can you kind of see a little bit of action? Anything? Much? Not much. Watch when I do it on this side though. Remember, that's neutral. You see how it's pulling it? Like, I didn't touch it. I just brought this nearby and I got it swinging. So this is somehow exerting a force on this one and really not being able to do it to this one. How do we explain that? Wait, well, I'm even cooler. Watch what happens if I let them touch. Now what's it doing?
Repelling?
Yeah, it's repelling, and now it's attracting. So it just depends on which, I gotta ground this. You're grounded. So when I bring this nearby and this is neutral, it still attracts it. How? If you understand this phenomenon, which is an everyday thing, you've all done this. Did you ever do the thing with you rub a balloon on your hair and then you stick it to the wall and it sticks? It's the same phenomenon. I can't do it anymore, I know. That's why I bought this. Anyway, does anybody know how this works? Why a balloon sticks to the wall, or why I'm able to take that kind of conductive ball and make it dance with a charged rod? Look at Jeffrey here. Oh.
Is it because like the aluminum molecules, some of them are like facing opposite ways and then they give it power?
You know, that's a good thought from what we've been talking today, but it's not that. Because aluminum, first of all, it's tin, literally is tin, it's SN. But second of all, it's not molecular, it's just a metallic solid. Any other thoughts? Let's look at it from how the balloon sticks to the wall, and then I'll apply it here. So imagine we have a wall. Not bad, right? And I'm going to draw a really simplified picture to show that the net charge inside the wall is zero. There's pluses and minuses from the nuclei and the electrons and all that, but it should be balanced. Now we have to understand the difference between two important words here. One is neutral, and the other one, well, let me kind of, no, I don't want to do that right. Versus charged versus polarized. Okay, three words. Okay? The key word here is polarization. That's what I need you to understand. If you had physics, you probably talked about this before. So let's say I rub the balloon, rub a balloon on my head. And let's assume it acquires a negative charge. So I'm going to put some excess negative charges on the balloon to represent that. What happens to the balloon? Oh, there now looks like both. What happens to the balloon and the wall as I bring these toward each other? Yeah?
The negative ions attract to the negative and positive ones.
Close. They don't. Negative doesn't attract negative.
Oh,
What is it?
it attracts to the positive ions, and the negative repels it, so that's why it repels it.
Very good. So when that happens, the negative charges near the balloon get pushed back, and the positive charges get pulled forward. Have I charged this up, or is it still neutral? What do you think?
Neutral?
How do you know?
Because it's like stock conditions for the ball negatives are all positives.
Yeah, they're still add up to zero, don't they? So this is still neutral. But Coulomb's law tells us that when we're closer to a charge, we feel the force stronger than when we're farther from a charge. So once this thing separates into charge, aren't these negatives closer to the positives than they are the negatives? And if that's true, there's more attraction than repulsion. So there's a net attraction here. What we're describing here is not charging up the wall. it's called polarization. We're saying this is polarized. So what's the difference? What does that mean? Neutral means no net charge, that adds to 0. Charged means there is a net charge, meaning that we have either a surplus of pluses or a surplus of minuses. Oops. So then what does polarized mean? By what I've been showing here, what do you think it means to be polarized? Because this goes right back to polarity in the molecule. Any thoughts? How about separation of charge? Okay? Let me show it in a simpler way. Is this charged or is it neutral, what I just drew on the board?
Neutral.
How do you know?
He's got a plus and minus, nothing else.
Okay.
It can't be charged.
Is it polarized or non-polarized?
Polarized.
Wrong.
Polar.
Not full.
How do you know?
There's one of each.
Well, I'll draw it again. Is there one of each now? Is this neutral?
Yeah.
Is it polarized or non-polarized?
Polarized.
But you said this was polarized.
But they're close together.
So is this polarized or not? This one.
Not full.
Why?
They're not separated.
That's it. When the center of plus and minus charge are the same, it's non-polarized. So like when you first encounter a neutral object that's not being acted on by any other forces, the charges are all balanced out and equally distributed. But if you bring something that has charge nearby, you can cause the distribution to change. That's what polarization is. Causing a separation of charge by bringing in some other source of charge to kind of move things around. So this is non-polarized and neutral. This is neutral but polar because of the separation of charge. And then if I wanted to show one that's actually charged, then I would have to show you a circle that had either just a negative or just a positive, or overall more of one than the other. But do you see now what I'm trying to show or not? So once we understand that concept, now I can show you how the last of the intermolecular forces work. Because this is really a puzzle if you think about it. Like, polar molecules attract through dipoles, fine. Then there's special ones that have this hydrogen bond. But why in the heck can two neutral nonpolar molecules ever stick together? What is the mechanism? Well, I'm glad you asked me that. Nobody asked. You know, if I'm going to have a hallucination, it might as well be my favorite. Okay. Here it is, ladies and gentlemen, the answer to all the questions. The mystery of the London dispersion force. Sorry. All right. When I rubbed this rod with a fur, it acquired a charge that let me polarize something next to it. London dispersion forces are extremely important because even though they're technically the weakest type of interaction, they can grow huge if you have bigger and bigger molecules with more and more electrons. So all molecules, whether they're polar or not, experience dispersion. The next bullet point says something about temporary dipoles. That is hard to imagine, so I'm going to show you a graphic that will be mobile so you can understand it. But for now, let's just assume for a moment that we have what was first a nonpolar molecule, and then for some reason it kind of just fluctuates and creates a momentary dipole, just because the electrons happen to shift one side or the other, just randomly moving. Well, as soon as there's a dipole in one molecule, if it's close enough to another one, it can induce or create polarity in the neighbor in that moment. And so, just like I showed how this pipe can induce polarity in the neighbor of this ball, one temporarily polarized molecule next to another one that's not can cause it to become polarized. And in that moment, they'll attract. But it's very temporary. It just flickers on and off because it's random. This is the best they could come up with to try to explain how nonpolar molecules can be liquefied. There doesn't seem to be any other way that we would be able to get them to stick. They're neutral, they're no polarity, they're completely distributed evenly, but they can fluctuate. What do you mean fluctuate? Well, I'm glad you asked me that too. Check this out. You see how that electron cloud's doing the mamba? That's just random. It's just the fact that electron clouds, although their time average is kind of uniformly spherical, there's fluctuations, just because the electrons are moving. So what, you might say? Well, every time the electron cloud randomly shifts, where the electron happens to be further toward is going to be temporarily negative, and where it shifts away from will be temporarily slightly positive. These are very small fluctuations, and they're happening rapidly at all times. So they add up to an overall average force. But do you see what I'm getting at by a temporary dipole? It just keeps fluctuating randomly, and moment by moment, it's creating that effect. But if there's a molecule next to it, it inspires or induces dipoles temporarily in the neighbors, and in those moments causes attraction. Yeah?
So what you just did, is that a dipole?
That was me temporarily polarizing this, yes. And then as soon as I take away the charged rod, this goes back to equally distributed. But you see, as it happens randomly in one molecule, it inspires the ones next door to polarize, and then they stick in that moment. But you can see why this is such a weak force. The degree to which that fluctuation happens can be really small, and that's why something like helium, you have to bring it down to 4 Kelvin before it can liquefy. So this effect can be the only force that holds helium atoms together, but it's so weak for helium that you have to be almost absolute zero before it's strong enough to hold them together. Gases like oxygen, a little stronger, right? Oxygen, wow, it will liquefy at a balmy like negative 180 degrees Celsius. Balmy. So there's a key point here. The strength of this force depends on the number of electrons, meaning the more electrons you have and the bigger the molecule you have, the more spaces and more fluctuations you can do. So for example, if you look at a big molecule like this, everywhere along the electron cloud, fluctuations can be happening. And the more of that that's happening, the stronger and stronger this dispersion force will be. Case in point, anybody cook? Okay, do you know what well, I do need a number. Which has the higher boiling point, oil or water? By far, right? Water boils at like 100 C, oils can boil 200 or 300 or higher. But oils are hydrocarbons, so all they have is dispersion, this weak little fluctuating force. Water has hydrogen bonding and dipole attractions, and dispersion for that matter. So what this tells us is as the molecules get bigger and bigger, the dispersion force can grow dramatically and overwhelm everything else. So you got to be careful when you make comparisons. Pound for pound, hydrogen bonding is the strongest type of intermolecular force of these. Then the dipole attractions, then dispersion. But dispersion can outweigh them all if the molecules get bigger. And we'll see evidence of that as we're going forward with the lesson. Yeah?
So do those electrons, they still move within the bonds, right?
Yeah. They're within their normal electron shells and all that. But again, at any given moment, they can be more in one point than another because they're in motion. They're not static. And that's why the more electrons, the more layers of electrons you have, the more places you can have these fluctuations and the bigger they can grow. So that, like I said, is the most subtle one. But please, again, keep in mind, all molecules do this to each other or with each other. Only polar molecules have dipole attractions, and only the NOF to H ones have hydrogen bonding. but we can use all of them depending on the molecular structure. So like if I gave you the structure, let's just do a simple alcohol. Oh no, we'll do it, this is an acid, not an alcohol. Here's a Lewis structure for an organic acid, acetic acid. Anyway, which type of intermolecular forces can this one interact with other similar molecules? Like if I was trying to explain this being a liquid, I'd have to have at least 2 of these molecules. But assuming we had at least 2 molecules, which types of IMFs could you imagine were involved in holding them together?
Hydrogen bonds.
Hydrogen bond, where? How do you know that? Where are you looking to show that hydrogen bonding can happen?
Because there's an oxygen and a hydrogen.
So this group will allow it to H bond to another similar molecule or one that can do that, right? This is not a hydrogen bond, right? This is a covalent bond. Be careful. Hydrogen bond would be if this was attracting to the hydrogen on the next molecule. But the fact that this structure has this allows it to be able to do that. That's important. Okay. What other types of intermolecular forces? Or is this the only one? Well, is the molecule itself polar? Does it look like it has polarity as a whole? Yeah. Doesn't it look like it could be polar around this section? So because of the general polarity in the bond, or in the molecule, that means that this molecule can also dip with other molecules. That's the dipole-dipole. And then, simply because it's a molecule with an electron cloud, all throughout, it can do the dispersion type of attraction as well. In this case, probably the most important of the 3 in this molecule is the hydrogen bonding. But in other molecules, that's not always true. We'll take it up from there next time. Today's lesson was mostly to show you the mechanism of these 3 types of intermolecular forces. So we'll finish that tomorrow, and then you're going to work on questions together as a class. Thank you. Have a good day. Was that okay, clarity-wise, or? I thought I was pretty good.
Wait, so hydrogen bonds happen, like that's an intermolecular force, right?
It's one of the 3 ones we talked about today.
Okay, okay.
That's right.
But